Hello students, a warm welcome to all of you. Today we are going to begin with periodic trends, second part in which we are going to discuss periodic trends in various properties such as electronegativity, valency, electropositive character, that is metallic character, and electronegative or non-metallic character in elements, and some of the examples based on the concepts we have discussed so far or are going to discuss in this session. The first property that we are going to discuss is electronegativity. It is denoted in brief as capital EN. We can define electronegativity of an atom as its power to attract the shared electrons towards itself. Now, since this property is associated with the behavior of an atom towards shared electrons, it is not the property of an isolated atom. The property of an isolated atom which deals with its attraction towards electron is known as electron affinity, which we have already discussed in Periodic Trends Part 1. There are various factors which affect the electronegativity of an element. The important ones are effective nuclear charge, atomic size, hybridization state of the atom, and the oxidation number of the atom. Now, the first one is effective nuclear charge. Electronegativity is directly proportional to the effective nuclear charge of the atom. As the effective nuclear charge increases, the attraction of the nucleus towards the shared electrons also increases, and thus the electronegativity also increases. The second important factor is atomic size. Electronegativity is inversely proportional to the size of the atom. Along with the increase in atomic size, the electrons move further away from the nucleus. Therefore, the attraction of the nucleus on the shared electrons also decreases, and thus electronegativity also decreases. The third important factor is the hybridization state of the atom. Electronegativity is directly proportional to the percent S character but inversely proportional to the percent P character of the hybrid orbitals in the atom, possibly because S orbitals are more closely located to the nucleus as compared to the P orbitals. Let's take the example of carbon. As we move from the sp3 state of carbon to the sp state of carbon, we can see that the percent S character increases from 25% to 50%, whereas P character decreases. Since electronegativity is directly proportional to S character and inversely proportional to the percent P character, we can see that the value of electronegativity also increases from 2.5 to 3.25. The fourth important factor is the oxidation number of the atom. Electronegativity is directly proportional to the oxidation number of the atom. When carbon is single bonded, its oxidation number is -4. For example, in methane. In double bonded carbon, for let's say ethene, that is CH2CH2, the oxidation number of carbon is -2. And in single bonded carbon, it is -1. For example, in ethine. Now, as the oxidation number is increasing, that is from -4 to -1, the electronegativity of the carbon also increases in the same order. It is observed in the periodic table that as we move across the period from left to right, the value of electronegativity increases along with the decrease in the atomic size. And when we move down a group, as the atomic size increases, the value of electronegativity decreases. This table shows the values of electronegativity for various elements on the following scale, using the intensity of the color to indicate their values. The low values are indicated by a lighter shade of blue, whereas the higher values are indicated by dark shade. As we can see in this table that as we descend down a group from top to bottom, the value of electronegativity decreases, whereas on moving across a period from left to right, the value of electronegativity increases. Fluorine has the highest value of electronegativity, that is 4. But there are certain exceptions to the periodic trends in the electronegativity values that we have just discussed. In the group second B, which consists of elements zinc, cadmium, and mercury, the electronegativity value increases on moving down the group instead of decreasing. Similarly, in group third A also, the electronegativity value increases from moving from aluminium to gallium instead of decreasing. And the electronegativity of francium with atomic number 87 is equal to that of cesium with atomic number 35, instead of the expected lower value of francium. Now, this is due to the fact that the increase in nuclear charge is somewhat balanced by the increase in shielding effect. Various scientists attempted to evolve a quantitative scale of electronegativity. So some of the important scales named after the scientists which developed them are Mulliken scale, Pauling scale, and Eldred and Rochow scale. So first of all, let's see what is Mulliken scale. According to this scale, the electronegativity of an atom is the arithmetic mean of its ionization energy or ionization potential, denoted by IP, and electron affinity, that is EA. So in the form of a simple mathematical formula, we can write that Chi, where Chi is electronegativity of the atom, is equal to ionization potential plus electron affinity divided by 2. Now, Pauling gave a quantitative concept of electronegativity based on the bond enthalpies. So according to Pauling's scale, for a molecule AB, Chi A minus Chi B is equal to EAB minus under root of the sum of EAA and EBB, where Chi A is the electronegativity of A, Chi B is the electronegativity of B, EAB is the bond enthalpy of the molecule AB, EAA is the bond enthalpy of A2, and EBB is the bond enthalpy of B2. Now we can relate Mulliken's scale with Pauling's scale with the help of the formula Chi Pauling, that is electronegativity on Pauling's scale, is equal to 0.336 into Chi Mulliken, that is the electronegativity on Mulliken's scale, minus 0.615. The third important scale is the Eldred and Rochow scale, according to which Chi AR, that is electronegativity on Eldred and Rochow scale, is equal to 0.359 Z divided by R square plus 0.744, where Z is the atomic number of the element and R is the atomic radius. Applications of electronegativity. The first important application is metallic or non-metallic character. If the electronegativity value of an element is low, that is, the element has a tendency to lose its electron, then the element will exhibit metallic nature. But if the electronegativity value is high, that is, the element attracts the shared electron towards itself, the element will exhibit non-metallic nature. The second important application is the ionic character in a covalent bond. So the percent ionic character in a covalent bond formed between atom A and atom B will be equal to 0.16 D plus 0.035 D square into 100, where D is the difference between the electronegativities of A and B. The third application is the acidic and basic nature of oxides. For an oxide with a general formula M2O, where M is the element and O is oxygen, if the difference between the electronegativity of oxygen and that of the element is less than 2.3, the oxide will be acidic in nature. But if it is more than 2.3, the oxide will exhibit basic nature. Now we can easily understand why is it so. An acidic oxide is that oxide which gives the solution of an acid with water. So that means that solution will furnish hydrogen ions. Now we know that the electronegativity of oxygen is 3.5. If the difference between XO and XM is less than 2.3, that means the electronegativity of M is also high. So in that case, it will easily attract the shared electrons towards itself and easily furnish hydrogen ions in the solution. Now those oxides which give the solution of a base with water are basic oxides. That means that solution will easily furnish hydroxyl ions. Now if the difference between the electronegativity of oxygen and M is more than 2.3, that is, the electronegativity of M is pretty low, this element will not be able to attract the shared electrons towards itself and will lose the electrons, furnishing hydroxyl ions in the solution. Therefore, these two conditions stand valid. Another application of electronegativity is the acidic and basic nature of hydroxides. Now, if a hydroxide AOH, where A is the element, is basic, it will furnish hydroxyl ions in the solution. But if it is acidic, it will furnish hydrogen ions in the solution. Now we know that the electronegativity of oxygen is 3.5 and that of hydrogen is 2.1. So this difference is equal to 3.5 minus 2.1 is equal to 1.4. Now GO is the electronegativity of oxygen and Ga is the electronegativity of element A. Now in case the difference between the electronegativities of oxygen and A is more than 1.4, that is, the electronegativity of A is low, it will tend to lose its electron and therefore hydroxyl ions will be easily furnished in the solution and the hydroxide will be basic in nature. But in case if this difference is low, that is, the electronegativity of A is high, it will tend to attract the shared electrons towards itself and will form hydrogen ions in the solution. Another application of electronegativity is the calculation of bond length. The length of the bond between atom A and atom B, which is denoted by DAB, is equal to RA plus RB minus 0.09 D, where RA and RB are the atomic radii of A and B respectively, and D stands for the difference in the electronegativities of A and B. Another important application is the diagonal relationship. Some elements of the second period show diagonal relationship with the elements of third period. Some of their properties are quite similar. For example, lithium shows diagonal relationship with magnesium. Beryllium shows diagonal relationship with aluminium. For example, the ionic radii of these elements, such as for lithium and magnesium, and for beryllium and aluminium, are almost same. The reason for this diagonal relationship is the similarity in their electronegativity values and therefore the similarity in their chemistry. Let us see what is the effect of electronegativity values on the chemistry of compounds. The electronegativity of sodium is 0.9 and of chlorine is 3 on Pauling scale. Now when the two atoms come together, that is come closer to each other to form a bond, due to the higher electronegativity value, chlorine atom pulls the electron, that is the outermost valence electron of sodium, to form sodium ion and chloride ion. Now these two ions are bound together by strong electrostatic forces of attraction. But when two hydrogen atoms come close to form a bond, there is no such difference in their electronegativity values. The electronegativity of both the atoms is 2.1. So when they come close to form a bond, there is no such difference which causes the transfer of electron from one atom to another atom. So both of them retain their electrons and then share their electron to gain stable configuration and thus form a covalent bond. Next property is valency. The combining capacity of an element is known as its valency. It is directly related to the electronic configuration of the atom. The number of electrons in the outermost orbital of the atom determines its valency. Therefore, the electrons present in the outermost shell are known as valence electrons. If we look at the position of an element in the periodic table, we can easily determine its valency in most cases. For example, in case of S block elements, the valency of the element is equal to the respective group number. For example, lithium. It is present in the first group, so its valency is equal to 1. Similarly, calcium is present in the second group, so its valency is equal to 2. In case of P block elements, that is group 13 to 17, their valency of the element is equal to the group number minus 10. For example, let's say boron. It is present in group number 13. So its valency will be 13 minus 10, that is equal to 3. Carbon. It is present in group number 14. So its valency will be 14 minus 10, that is 4. The D block elements, that is the transition elements occupying groups 3 to 12, have variable valency.